All right, let's begin with charge. What do we know about charge? Well, there are basically two types of charge. There is positive charge and there is negative charge. Now, charges comes in all shapes and quantities of charge, but if you break down positive charge, you end up with essentially a proton. Now, in this class, a proton then represents the smallest amount of positive charge that you will encounter. The smallest amount of negative charge that you will encounter is an electron. Okay. Now, for the sake of full disclosure, protons are actually made up of quarks. Specifically, they're made up of two ups and a down. And each one of those has a fractional amount of charge that when you sum it up, it equals the amount of charge that's on a proton. Electrons are not like that. As far as we know, electrons are individual, non-divisible particles. Of course, future science may change that idea. Okay, so you've got these two types of charge, positive and negative charges. And like I said, as far as we're concerned in here, a proton and electron are the smallest amount of those charges you can have. That means that these charges are quantized. Quantized means that any amount of charge that you can think of must be some integer multiple of these two. Okay, so if you want to have one proton or two protons, that's fine. 3, 10, a billion protons is fine, but you will never have 2.5 protons. You'll never have 2.3 protons of charge. So that's what is meant by quantized. That charge comes in discrete packages. Charge is also conserved. Just like momentum is conserved or energy is conserved, charge is also one of those things that's conserved. Now, what does that mean? That means that before an event happens, whatever amount of charge you have is going to be the same after the event happens. Just like conservation of momentum, the total momentum before the event is equal to the total momentum after the event, even though that may have been changed due to the event. The actual absolute total before and after is the same. Well, the same is true here for charge. You cannot just willy-nilly create charge out of nothing. You have to get charge from somewhere else, okay? So there has to be a before in order for there to be an after when it comes to charge. Now, there are some exceptions to that in the quantum mechanical world. Let's say this represents a photon of light and it's traveling along. Well, a photon has a net charge of 0. It is possible for photons to undergo events where they generate particles, events called pair production. And in that case, they must generate positive and negative charges in equal amounts, so that the total amount of charge is equal to the same that it was before, 0. So that's not really the creation of charge out of nothing. That's a transfer of energy from photon energy to electrical energy, but the total charge is the same before and after. Okay, let's get back to our protons and electrons here. They have exactly the same charge, so if we allow Q to represent the charge of a proton, we'll put a subscript P here, that's the charge of a proton, that's equal to Q for the electron, but the polarity is different. So one is the opposite of the other, one is the negative of the other. So the proton and electron have the same charge, but they have opposite polarities of that charge. Okay? Now, that's true of charge, but when it comes to mass, the mass of the proton is nowhere near the mass of the electron. In fact, it differs by 1836 times. So a proton is 1836 times more massive than an electron. Now, when it comes to the way that these charges interact, you learned this probably in 8th grade somewhere, that if you have a positive charge and it is near another positive charge, that those two charges are going to repel each other. So likes repel, and then opposites attract. So if you have two charges that are opposite, they're going to attract each other. If you have two charges that are the same, they're going to repel each other. So with that bit of information there, you know everything there is to know about charges. Okay, everything else is details. Now those details matter, and those details can be complicated, but nevertheless, everything is pretty much based upon this right here. So if we have charges that are moving through a conductor, we have a flow of charge. That is called a current. And if we separate charges, it also creates something called a potential difference. Now, current is going to be symbolized with the letter I here, and potential difference is going to be symbolized with the letter V here. So these two, I and V, that stands for current, and this stands for potential difference, which has another name, common name of voltage. So we will talk about currents and voltages as we go through the course. I just want to introduce the idea here that pretty much everything that in our modern society that works off of electrical energy in some way utilizes charge flow or charge separation in order to function. So you need to be aware of that sort of thing. We'll mathematically define each of these a little later, but I'll go ahead and tell you right now, because you guys are really smart students, that I is dq dt. dq dt, that's charge per time. So that's the derivative of charge per time, or the rate of change of charge per time. So if you have charge that's moving, flowing through a conductor, and you set up a marker and you count the number of charges that pass by in a second, then that amount of charge per second is the current. Voltage, similarly, but maybe a little more difficult for some people to understand, at least at the beginning here. Voltage is du dq. That's the rate of change of energy per charge. And that's a little more complicated to understand. It's not beyond you, but at this point, I don't want to go into great detail about how that works, but I will say this. If you separate charges, let's say you have a bunch of positive charges over on this side and a bunch of negative charges over on this side. Well, each of these charges has electric fields associated with them, but the electric field between these is going to point in that direction. Again, we'll learn more about this as time goes by. If you take another charge, let's say you put a charge right there, then that's going to be affected by this field. The amount of energy that it takes to move that is related to this, okay? Like I said, we'll talk more about that when we get there. I just wanted to introduce the very idea to you, all right? Okay, so we've talked about charge. We've talked about how it is quantized and conserved. We've talked about how protons and electrons have the same charge but opposite polarities, but they have considerably different masses. We talked about how like charges repel, unlike charges attract each other, and we've introduced this idea of current and voltage. Okay, let's move on and talk about a slightly different topic here. Let's talk about electrical conductors. Conductors, to put it simply, are materials, usually these are going to be metals, that allow electrical charges to easily flow through them. If the charge is able to easily flow through it, it's a conductor, regardless of what it is. So there are some things that make up, that are good conductors. If you look at a periodic chart of elements and you look at the element copper, we often think of that as a good conductor, and it is a good conductor. But what makes it a good conductor is it has one valence electron in its outer shell, and if you knock off that valence electron, which doesn't take much energy in the case of copper, then that electron will flow, as well as other electrons in the copper material will flow, and that makes it a good conductor. Now, there are other conductors, there are other elements that have one valence electron. For example, chromium has one valence electron, but chromium, that electron is pretty tightly bound. It's not as easy to knock off as it is for copper. Now, if you heat up chromium, then that heating it up helps that electron become free. So chromium becomes a better conductor at higher temperatures. So it makes a pretty good high temperature conductor. And if you look back over here at copper and you go down the chart here, what you'll see is that you got silver, you got gold. Those are really good conductors as well. So everything in this column here is a pretty good conductor. Okay, so those are the things that we normally think of as conductors. Those are going to be things that allow charges to flow easily through the conductor. Now, I stress that word through. It's not necessarily flowing on the surface of the conductor, it's flowing through the conductor. All right. Well, then, enough about conductors. Let's talk about insulators. Insulators are really non-conductors. So anything that's not a conductor is probably going to be an insulator. Insulators we typically think of as more compound substances, not just pure elements like you would find in a periodic chart necessarily, but things like glass, things like plastics, things like rubber. Those are non-conductors, and for the most part, non-conductors make good insulators. So these two terms here are kind of opposites of each other. You've got conductors and insulators, or conductors and non-conductors. All right, so you can divide elements up into those types of categories. But also in the periodic chart, there are other elements that are semiconductors. Now, semiconductors have certain electrical properties. If you were to modify the semiconductor material, then that's a process called doping. And whenever you dope a semiconductor, well, you might turn it into a conductor, or you might dope it another way and turn it into an insulator. And by being able to layer these conducting and non-conducting layers next to each other, you can create all sorts of interesting things like little transistors. Because doping can be done on a microscopic scale, you can cram lots of transistors, and a transistor is just a little switch. You can cram lots of these electrical devices into a tiny little area, and that allows us to create our modern day semiconductor devices like computer processors. If you're carrying a cell phone with you, then that has semiconductor material in it. So where are the semiconductors on a periodic chart? Well, they're going to be in the area right around here, in this area right around here. And usually semiconductors can be mixtures of more than one of these. Silicon, you may be familiar with that one, is a good semiconductor. Some of the others in this area are also good semiconductors. Okay, but then there are also elements called superconductors. Now, superconductors are kind of odd, and I can honestly say they're not fully understood yet as far as the physics of how superconductors work. There are probably lots of surprises left to those people that want to study superconductors. But superconductors possess a property so that if you change something about the substance, then it offers no resistance to current flow. Let's talk about what resistance is here for just a minute. Let's say this represents a piece of copper wire. Okay, well, copper, if you look at it on a periodic chart, has how many protons? Copper has 29 protons. And although I don't necessarily know how many neutrons it has, it's somewhere around 29 neutrons. Okay, so you've got 29 protons. So let's say you got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29. There's 29 protons. Now add to that 29 neutrons. That represents then one nucleus of a copper atom. All right. So all of those are bound together by the strong nuclear force. They're not going anywhere. However, surrounding all of those in a neutral copper atom, you're also going to have 29 electrons. Remember, the outer one is the valence electron, and it is not as tightly bound as the others are. So you've got all of these nuclei. I'll just draw a bunch of nuclei here. Those are the 29 protons, 29 neutrons bound together. They're not going anywhere. Okay, the electrons that are on the outside, the one valence electron, which is pretty easy to knock off, is going to be the thing that moves through this copper. But as it moves, let's say this represents an electron coming along here. As it moves, it collides with the nuclei. Boom, 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 boom. And as it collides, it is in general heading down in one direction. And that direction would be the direction in which the potential difference allows it to move. So it is making collisions all along the way. Well, those collisions release energy, and that energy usually comes out in the form of heat. So that heat energy that is generated as a result of these nuclei resisting the flow of the electrons, that's what resistance is. So that is how resistance is created. Resistance is opposition to the flow of electrons. Well, and that generates heat. Well, in the case of a superconductor, if you lower the temperature of the superconductor, then resistance goes away. One of the first superconductors to have been discovered is actually mercury. And if you lower the temperature of mercury down to a certain level, then it just so happens that these structures in here arrange themselves in such a way, and we're not quite sure all the details because it may be electron pairs that move here, it may be single electrons, it may be a mixture of these things, but it turns out that it goes right straight through, no resistance whatsoever. And that's an unusual thing. Superconductors would be pretty important then if you could create one that works at room temperature. And if that happens, it's going to revolutionize the world. It's going to be one of those things that changes everything. Because once you get rid of resistance like this, you get rid of waste. So imagine power lines spread throughout a city. Once you put some electricity into them, you don't need to really put much else except maybe what's lost by the consumer on the consumer end, because there would be no resistance in the electrical lines. That would that might lower your electricity bill quite a bit. Okay. Well, we've talked about conductors, we've talked about insulators or non-conductors, we've talked about semiconductors, and we talked about superconductors. So these are all electrical properties, and elements can take on one or maybe more of these categories here. So you can divide up the universe into these categories of electrical properties there. Okay, well, let's move on then. How charge distributes itself on a conductor. So let's say that we have a nice spherical conductor here, and by some mechanism you are able to put a bunch of positive charges at the center of that conductor. So this is a sphere, and forget about the mechanism that allows you to do that. You can use magic, whatever, but you put some positive charges right there at the center. Now, what's going to happen when you let go of those charges? You put them there and now you let go. Well, what's going to happen is that those are positive charges, and this conductor, we're going to assume is a conducting sphere, so those charges are free to move. And what's going to happen is that they're going to try to get as far away from each other as possible, and as far as they can get is going to be out here on the surface like this. Okay, so all of those charges moved away from each other and distributed themselves on the surface to try and get as far away from each other because of their natural repulsive tendencies. And that distribution is going to be uniform on the surface. So what does that mean? That means if you have charge anywhere on inside a conductor and there's no motion, in other words, this isn't a current flowing, continuously flowing, that those charges are going to try to get as far away from each other, which means they're going to move out to the surface. So regardless of the shape of this conductor here, those charges are not going to stay inside the conductor. They're going to move out to the surface. Now there's a lesson there. That's the important lesson. If you have a conductor and that conductor is charged, then the charge is on the outside of the conductor, not on the inside of the conductor. Now that's true as long as you don't have a current flowing through the conductor. Where does the charge live? It lives on the outside. And the same would be true if you had some weird shape. Let's say something, kind of like that. You had some weird shape and you put charge at the center here, like that. And now where's it going to go? Well, it's going to move out to the surface, but because this is no longer a uniform, nice spherical shape, you're going to have an uneven distribution of the charge. And it turns out that charge is going to concentrate more at these sharp corners and the sharp edges like that. Doesn't mean there won't be charge in here in these smooth edges, but there's going to be more of a charge buildup at the sharp corners. And that's just the way the charge works. What's going to happen in order to cause that, what's really happening is the charge is distributing itself in such a way so that the net electric field on the inside is zero. That's the electric field. We haven't talked about that, but we're going to really soon. And the same would be here. The charge is distributing itself in such a way that the electric field on the inside is zero. So two rules of thumb that you should keep in mind from this brief discussion here. One, charge lives on the outside of a conductor as long as it's electrostatic, meaning that no current is present. And the charges distribute themselves in such a way that the net electric field on the interior of the conductor is zero. So electric fields inside conductors, as long as we're in an electrostatic situation, is going to be zero. Okay, that's the lesson there, and with that we'll move on to something else. All right, so let's say that we have a positive charge here. And let's say that that is a proton. That's the smallest amount of positive charge we can have effectively. Well, the proton and the electron have the same charge but opposite polarities. So what is the amount of charge that they have? We'll call that the electronic charge. And we'll symbolize that as a small letter e. So this small e notice it says electronic, it does not say electron charge. So that e is going to be positive for a proton, it's going to be negative for an electron. So a proton has a charge equal to plus 1e. And the electron has charge equal to minus 1e. Okay, well that e has a value itself. And in the SI system, E is equal to 1.6 times 10 to the minus 19th coulombs. So that capital C right there, that is the unit of charge, and it is called a coulomb. You spell that C-O-U-L-O-M-B, like that, coulomb. So 1.6 times 10 to the minus 19th coulombs, if that's positive, is the charge on the proton. Negative 1.6 times 10 to the minus 19 coulombs, that's the charge on the electron. Now that's a tiny, tiny amount of charge, 10 to the negative 19th, a very, very small number, okay? But nevertheless, that's what it is for proton electron. This is the electronic charge. Okay, well, we're going to symbolize charge in here, and we've already introduced this with the letter Q. So Q is what a charge variable will be. So Q could be some number like 5,000 coulombs, okay? And that's a lot of charge. But that's an example of a charge value. Now, if we have, let's say, two charges here, we'll call this one Q1, we'll call this one Q2. Now, you don't specifically know which one's positive and which one's negative just yet. I haven't told you that information, though. But if they're separated by some distance, and let's call that distance R, there's going to be a force. And that force is either going to be attractive if these two are opposite polarities, or it's going to be repulsive if they are same polarity. But the direction of that force, if I draw a line right through these two charges like that, the direction is somewhere along that straight line. It's either going to be towards each other or it's going to be away from each other, but it is along that line somehow, okay? Depending upon if they're like polarities or opposite polarities. But nevertheless, there's going to be a force. Well, let's call that force F. And that force is going to be the force in newtons. And R is the distance. So this was the force. This is the distance between the two charges. And we've already defined Q as the variable that we will use for charge. All right, well, these two things are going to interact, and the law with which they interact is called Coulomb's law. And what this does is this describes the nature of the interaction. It does not explain why they interact this way. It just is a description of how they interact. And how they interact then is given by this equation. F equals 1 over 4 pi epsilon naught Q1 Q2 over R squared. Okay, now there are lots of, there's another symbol here that you don't recognize, and that is epsilon naught. Epsilon naught is called the permittivity of free space. Permittivity of free space. Now, free space is just another word for vacuum. So this term is the permittivity constant for vacuum. And that has to do with how the nature of the surroundings of how these two things interact. If we were not in free space, then the permittivity constant would change. But it is a set value. Epsilon naught is a known value, and it is 8.85 times 10 to the negative 12 Coulomb squared per Newton meter squared. That's the value for epsilon naught. Now, if you look at this value and you plug it in here, you'll notice that this whole first term here is really a constant. So 1 over 4 pi epsilon naught is really a constant. And if you take 1 over 4 pi epsilon naught, plug it in, you end up with 8.99 times 10 to the 9th Newton meter squared per Coulomb squared. So this is often just rounded to 9 times 10 to the 9th Newton meter squared per Coulomb squared. And it's given a value just called K. So oftentimes you will see Coulomb's law written as K, Q1, Q2 over R squared. Okay, now I have to be careful here because remember, a force has both a magnitude and direction. This is really just for the magnitude. So your textbook does this. It puts absolute values around the Q, and that way it doesn't matter if you have positive Q or negative Q, you're always going to have a positive value for the force. So this will be how you figure out the magnitude of the force. The direction of the force you have to figure out on your own. And remember I said the direction is going to be along this line, either towards each other or away from each other, depending upon if these are positive and positive, or negative and negative, or positive and negative. So if they're like, they're going to repel each other. If they are opposites, then they will attract each other. So direction you figure out one way, magnitude you figure out another way using the equation here. All right, so that is called Coulomb's law. Now let's use it real fast and work one problem, and then we'll probably work more of these in class when you show up. But we'll do a really simple problem here. In fact, so simple that I almost don't want to do it. But let's say here's Q1, here's Q2, and they are separated by some distance r. And let's give some values. Let's say r is 1 centimeter, Q1 is 3 microcoulombs, Q2 we'll say is negative 2 microcoulombs. Okay, so one's a positive, that one's a positive, and Q2 is a negative. So what does that mean? That means these two things are going to be attracted to each other with some force F, like that. Okay, so we know the direction. We just figured out the direction based upon the polarities of the two charges. Then if we say, I want to know what is the force on Q1. Okay, well, we will use Coulomb's law to calculate that. F equals K Q1 Q2 over r squared, and we would plug in our numbers now. Now, anytime you do a calculation in class, you have my permission to round K to 9 times 10 to the 9th Newton meters squared per Coulomb squared. Now, if you're doing a calculation for a homework problem, maybe you could just program it into your calculator to be the 8.99. But 9's not going to make a big difference to us. Okay, so Q1 is 3, and it's micro, so that's 3 times 10 to the negative 6 coulombs, multiplied by Q2, which is negative 2 times 10 to the negative 6 coulombs. Now, take the absolute value of that, divide it by r squared, which is 1 times 10 to the negative 2 meters. Don't forget to square it, okay? And I did write that, see? So it's K Q1 Q2 over r squared. So we are ready to plug in our values and do calculation, computation. And when I do that, I end up with 540 newtons. So the force of attraction is 540 newtons. Now, remember, anytime you write a force, it's going to must have a magnitude and a direction. This is the magnitude. Well, how do I specify what the direction is? And the easiest way to do that is just to say it is attractive. So there, put a box around your final answer. This is the force that we're after. So this is the force on Q1 due to the presence of Q2. Now, if I asked it the opposite way around, what is the force on Q2 due to the presence of Q1? The answer is still the same. It is an attractive force, and it's still going to be that value. In fact, that's Newton's third law. Charge distributions. As we get into the class, we will move away from Coulomb's law and move on to more complicated situations. Let's still rely upon Coulomb's law in order to figure out solutions. Now, Coulomb's law, you've been using the symbol Q for charge, but specifically that is a point charge. Now, a point charge has a unit of coulombs, and it really represents a point. So the charge itself has no physical dimension to it. It is truly just a point. So all of the charge reduces down to effectively a point in space. And we'll use the symbol Q to represent that point charge, and it has a unit of coulombs. However, as we go into this, we're going to encounter more difficult or more complicated charge distributions. One of the first ones that we will encounter is called a line of charge. And a line of charge will have a linear charge distribution. Now, a linear charge distribution will symbolize that as the Greek letter lambda. And it has so much charge per length, charge per meter. So you imagine that here's a line, and that line is composed of positive charges like that. Okay, well, if you were to cut the line here in between there, you would have a certain amount of charge per length. If I cut it somewhere else and maybe I cut it a different length, well, it still has the same amount of charge per length. So lambda in each of these cases would be the same for those sections that I've got drawn there. The same number of coulombs per meter. In that sense, it's kind of like a charge density, except it's a linear density. It's the amount of charge along the length there. You know, if you talk about mass density for a substance, let's say we're talking about gold. If you have a block of gold, you know, that block of gold has a certain density, and that's the density of gold. But if I take a chunk of it, that little chunk right there, and I pull it off over here, then that chunk has the same density as the big chunk. In fact, you cannot change the density of gold without making it another element. You know, gold, as long as it's pure gold, all has the same density. Well, the same sort of thing applies here. That if that linear charge density is the same, then this coulombs per meter is going to be the same as this number of coulombs per meter. Okay, now you can expand that idea to not just a line, but also a surface. So we could have a surface charge density or charge distribution. And what would that unit look like? Well, that's going to be coulombs per area or square meter. So you're talking about a surface area here, and maybe you got a bunch of positive charges on that surface. Well, how much charge per square meter? If the surface charge density is the same or is constant, then it's going to be the same everywhere. So if surface charge density is a constant, you're going to have the same surface charge density in this area as you would in that area. Okay? Now we'll symbolize that with a small Greek letter sigma for surface. Okay, and then we come to the next progression here, which is going to be volume. So a volume charge density or charge distribution. And what do you think the unit for that one looks like? It's coulombs per volume, which is cubic meters. And the unit for that, or I should say the symbol for that, is small Greek letter rho. Looks like a P, but that's a Greek letter rho. And in that case, you're talking about something that like a spherical volume. And you have charge maybe distributed all throughout the sphere, not just on the surface, but throughout the volume of the sphere. And if it's the same volume charge density, you would have the same volume charge distribution in that area as you do in that area as you do in any other area like that. Or I should say not areas, but volumes, any other volumes like that. So we will encounter these as we go through, and this serves as sort of a heads up of what is to come. Okay, next topic, and we're sort of introducing topics here early on, and then we'll dive in deeper into these. I want to talk about shell theorems. Shell theorems have to do with shells of charge. And what do I mean by shell? I mean something like, let's say this was a sphere, and you carve out the interior of the sphere until you've just got the shell. And then that would be charged. Now, I don't mean that there's like an honest-to-goodness shell here, honest-to-goodness metal surface there. That could just be the charge arranged in the shape of a shell. So in other words, the charge is out here as if it were a shell, and there's no interior portion to it. So this will be a shell of charge. And even though I kind of made it womp-sided here, for the most part, we would talk about uniform distributions of charge, uniform charge shell. So here, there's really only two shell theorems that we will talk about, but here's the first one. It says that a shell of uniform charge acts upon a charged particle that is outside the shell as if all the shell's charge were concentrated at its center. In other words, if I had a shell of charge, now let me sort of draw a circle here and then put positive charges on that. So there's my shell of uniform charge, and it's going to act upon a charged particle that is outside the shell. So in other words, let's say over here, there's another positive charge right there. As it's going to act upon that as if all the shell's charge were concentrated at its center. In other words, it's going to act as if all of that charge right there, and let's say there are n positive charges there. So the total charge of that shell is n e. E is the electronic charge. And this one over here, if that's a proton, then this would just be 1e. It's going to behave as if all of that were reduced down to a point charge that had a charge of n sub e, and this one remains 1e. So this problem right here you can solve. You can solve this using Coulomb's law. You know, that F equals K Q1 n sub e times E over whatever the distance between them squared is. So you could figure out the direction. This is going to be repulsive. So if you drew a line between those, it's going to be repulsive away from each other. And the magnitude is going to be given by this. If you knew what n was, you do know what E is. If you were given a value for R, you can compute the force, the magnitude of the force. Okay? Well, that's what this shell theorem says here. It says that a shell of uniform charge acts upon a charged particle that is outside the shell as if all the shell's charge were concentrated right at its center, right there. Now, you'll think, why does that happen? Okay, well, if you were to think of this as just a bunch of point charges arranged in the shell, and you were to do work that problem one at a time, let's say that's going to be, oops, I shouldn't have drawn it that way. It's going to be a force this way, it's going to be a force this way, force this way, force this way, force this, and you were to add up all of those, what you would discover is that these vectors, which can be broken up into components, you know, this vector can be broken up into a component that's downward and horizontal. This one up here can be broken into a component that's upward and horizontal. And you would discover that these vertical components here actually cancel each other. And that would be true for all of these. The vertical components actually cancel. So what you're left with is just the horizontal components here. So in the end, you end up with a force that is pointed that way and a force that's pointed that way. So all of the, you know, if you were to work this problem out, spend a lot of time working this problem out, you would discover that those vertical components cancel, the horizontal components are left. And that's really what the shell theorem is saying. That all of that distribution of a uniform charge distribution is going to act just like it's a point charge at the center of the distribution, and that's a problem that you know how to solve. That's the first shell theorem. So quite often, what appears as a complicated problem reduces down to a very simple problem once you apply the shell theorems. All right. So that's the first shell theorem. I said there's two of them. Here's the second shell theorem. If a charged particle is anywhere inside a shell of uniform charge, there is no net electrostatic force on the particle from the shell. Now, what that one is saying is that if I have, let's draw a shell here with some positive charges on it. And then I have a point charge that's inside the shell. Let's put a point charge right at the center because it's easier to understand if it's at the center. Then that charge right there experiences no net force due to the shell. What that means is if there's a charge on this side, then, and it's a uniform distribution, a continuous charge distribution here, then there's going to be another charge on the opposite side. And those two forces are going to cancel each other out like that. And the same in that direction and the same in that direction. So there's no net force. Now, you understand that probably if we place the charge at the center, that all of those forces are going to cancel each other out and the net charge on that particle at the center is going to be zero. And it wouldn't matter if it's positive or negative, it'd still be zero. Okay, but that's not what the shell theorem says. The shell theorem does cover that case, but that's kind of a special case where the particle is at the center. It says anywhere inside the shell, there is no net force on that particle. So let's try to explain that one. We won't go into it mathematically, but I think you'll understand it here. Here's the shell, and let's put the positive charges all throughout the shell. And remember, this is uniformly distributed, so even though it may look like my plus signs are not the same in all directions, it needs to be a uniform shell of charge. And let's place a particle off to the side here. Okay, so it's no longer in the center at this point. Well, you could go in and calculate using Coulomb's law what the force should be here. It's a little more complicated equation. F equals K Q1 Q2 over R squared, but you've got this continuous distribution of charge around here. You can't just treat everything like it's a point charge. Well, I suppose you could, but it would take you a very long time to work the problem. So what you can do is you can think of this as a line that way. Let's draw another line that way, right there. And that's centered at where they cross right at the center right there. Well, if you take the amount of charge that's in this area here and the amount of charge that's in this area here, and you perform the calculation, and you can do this and make that angle small, as small, incrementally small, infinitesimally small as you want to, so that you could do the calculation and then integrate around the whole surface area that's inside the shell. You could do it that way, but notice what's happening here. The distance from here to here is related to how big this area is. And the distance from here to here is related to how big this area is. So you've got distances and you've got areas. So you could say, okay, this would be my area. Let me just call it area 1, area 2. Like that. But then you've also got length 1s and length 2 here. And those two things work together. So the force is going to be related to, well, first of all, 1 over the distance squared. But it's also, you need to realize that the charge that goes on top here, the charge is related to how far away it is. So how much charge you include in your calculation, at least initially, before you integrate over the whole thing. And you would eventually integrate over the whole thing, but at least to set up the equation, you need to know how much charge is in there. And that chart, the amount of charge there, is related to that distance that the charge is away. So it's related to R squared. Now, what does that mean? That means that the charges on top are going to end up being R square related, divided by a distance, which is going to end up being R square related, and those two things will cancel each other. So what does that mean? That means you've got a constant zero value for the force on this thing. Okay? And even though perhaps maybe you didn't follow along with that, you could just trust the shell theorem because it does hold pretty well. Now, here's an interesting thing. This applies to the charge at the center of a charged shell, but it would really apply to anything where this force is going to be an inverse square law. So this would also apply to gravitation. So if you found a planet, let's say you found, if Earth is hollow, all of the mass is out here on the exterior portion, and the Earth is hollow, and you were to be able to go to the interior, then you would experience no force there at any point, not just at the center, but at any point inside here. You would have no net force acting upon you, so you would be weightless in that area right there. Okay? All right. Well, those are the two shell theorems, and I thought you should know about those. That will, knowing those will help simplify some of the homework problems that you will encounter. All right, let's move on now and let's talk about charging things. We've talked about how charge is conserved. So when it comes to charging things up, you have to get charge from someplace, or you have to separate charge. Well, there's a couple of ways to actually charge things, and one of them is by contact. Contact is essentially friction. If you have, you know, a body or a glass rod or something that has some charge on it, like this, okay? And you want to charge another body over here, then all that you really need to do is put these two things in contact with each other. And what's going to happen is that charge is going to distribute itself all over the surfaces here of that, okay? And then if you take it and separate it, well, now this one has less positive charge on it, and this one has positive charge on it. In fact, it's probably going to have the same amount of charge as this one. We're assuming that these are identical conducting surfaces, that those would be identical conducting surfaces when they come into contact with each other. The charge is distributed uniformly, so these have to be uniform surfaces in order for our example to work here. And the amount of charge on the left and the amount of charge on the right are going to be equal. But the total charge, whatever you had up here initially, is going to be split between these two now. Now, that's not exactly the same. That's not exactly the same if one of these is not a uniform surface, okay? But this is an example of how you can charge something by contact. Now, when I say charge something by friction, that would be an example of taking something like a glass rod or maybe a plastic rod and rubbing it with material like, let's say this is wool, okay? And you rub it real hard. Now, before they make contact with each other, everything is electrically neutral. But when they make contact with each other and you scratch the rod here, what happens is you're using friction and you're literally removing some electrons. So that when you move the wool cloth away now, this rod has some positive charge on it, okay? And the wool then is going to have some negative charge on it. So previously, the net charge before they made contact with each other, the net charge was 0. Okay, well, what is the net charge after they make contact? So after you're done rubbing the wool on the rod and you separate them, well, whatever positive charge you have down here, you have an equal amount of negative charge on the wool now. So what's the total charge? Still 0, okay? So that's one way that you can charge something. Contact, which is an example here, but also this is an example of contact as well. You're just exchanging charges. What you're doing is you're redistributing the charges. You're not creating charge, you're just redistributing charge that's already there. Okay, now there is another way that you could charge something, and this is called induction. And the way it works is, let's say that you have a sphere Again, uniform conducting sphere, and it has some negative charge on it. Okay, and you bring that close to another neutral conducting sphere, and it's neutral. Now, neutral doesn't mean it has zero charge. Neutral really means it has just as much positive as it does negative. So if it's got, 3 positives, it's also got 1, 2, 3 negatives in there. Okay, so it's got just as much positive as it does negative, and we call that neutral. All right, now let's bring these two close to each other. So the negative charge is going to still be distributed, but what's going to happen is the positive charge is going to run to this side of the conductor. The negative charge is going to stay on that side of the conductor, or run to that side of the conductor. Now, why are they doing that? Well, the positive charges, that we're assuming this is a conductor, so charges are free to move through the volume of the conductor. The positive charges are going to run to this side to be close to the negatives that are on this. And the negatives are going to try and get as far away from the other negatives, so they're going to go over here. So you've separated your charges then by doing that. Okay. Now, in actuality, remember, you as a good physics student, you understand that it's the electrons that are moving. The electrons are moving over here to the right-hand side, so you create an excess of electrons over there, and you have a deficiency of electrons here on the left-hand side, so that looks like positive charge over there. And that's actually what's going on. But it's okay to think about positive and negative charges moving here. It's exactly the same. There's really no difference between a positive charge going in that direction and a negative charge going in that direction. These two things are effectively the same. Okay, let's get back to our example here, though. We've got negative charge over here, and it may be that a lot of those negatives also move over on this side as well, like that. To be close to the positives. Now, let's bleed off some of the charge from this one. Remember, it's neutral. It's still neutral in this case. But if I hook a wire up here and I put that wire down to ground, or just down to, when I say ground, I mean literally the earth, the ground, and I plug it into the ground, what's going to happen is those charges that want to get away, the negatives, now have an additional path where they can flow. So what's going to happen is those negative charges are going to run down here. And what we've got after that, after you pull away the wire then, is you've still got this that's negatively charged, but now you've got this that's positively charged. And why? Because the electrons ran away. And if you separate these two things, then this one, you separate the two balls now. This one over here on the left is still negatively charged, and now this positive charge redistributes itself once they're separated, and you've got it positively charged. So initially you had something that was neutral, and now you've got something that's positively charged just by bringing it close by and then draining off the negative charge. That process is called induction. When the negative charge gets close to the neutral, you have a redistribution of charge here. And then you bleed off that, and it induces a positive charge on your final substance here. Okay. Remember, as a good physics student, you know that it is the electrons that move, but again, it's possible to talk about positive charges moving as well, because there is effectively no distinction between positive going one way and negative going the other way. Now, there is a difference. There is a difference because the negatives are actually moving, but from a measurement perspective, if you had to measure a current, there's no difference between measuring a current going of electrons going to the left than there is measuring a current of protons going to the right. Okay, one other thing before we close out this video. We've talked about the gravitational force, and we've talked about what's called the electrostatic force. Now, electrostatic means that it's electrical force, but it is for charges that are stationary or not moving. So if something is non-moving, then it's static. You may end up taking, if you're an engineering major, you may end up taking an engineering mechanics class, which is called statics. And the objects are not accelerating in those cases, so moving or moving with constant speed. That's the nature of electrostatics. Okay, But we've got the gravitational force and the electrostatic force that are working here, which is really the electromagnetic force. Which one is stronger? We can do a calculation to figure out which one is stronger, and that's a pretty straightforward calculation. So let's say that we reduce it down and we have one proton over here, okay? And over here, some distance away, we have one electron. Okay, we got a proton, we got an electron. And let's make it a nice number here so it'll be easy for our calculation. They're 1 meter apart. Now, these two things have mass, so we know the mass of the proton is going to be 1836 times the mass of the electron. If you were to actually go look that up, the value for the mass of the proton is 1.67 times 10 to the negative 27th kilograms. And if you go look up, that's the mass of a proton. If you go look up the mass of the electron, it's 9.11 times 10 to the negative 31 kilograms. Okay, those are actual values. Got those out of the textbook. I do not have those memorized. Okay, well, then in that case, let's figure out what the electrostatic force of attraction, and that's Coulomb's law. F equals K Q1 Q2 over R squared. Now, K is 9 times 10 to the 9th Newton meter squared per Coulomb squared. Q1, let's call that one the proton, and that's going to be 1.6 times 10 to the minus 19th coulombs. Well, what is it for the electron? Well, it's exactly the same, so we need to square that. Divide that by the distance between the two, which is 1 meter. We need to square that as well, but I got it up here. Okay, so what do we end up with? Let's put an E on here so that we understand this is the electrostatic force that we're computing here. And whenever we do that, let's see, what value do I get? You should check me on every calculation I do, but that's 2.304 times 10 to the negative 28 newtons. Okay. All right. That's a very small force, but you would expect that for one proton and one electron with such tiny charges, that would be the electrostatic force. Okay. But what about the gravitational force? Now, they also have mass, so that means they're going to be attracted gravitationally. So we should be able to do a gravitational calculation. Let's call that F sub G, and that's capital G, M1, M2 over R squared. Now, capital G, this is a number that I can never remember. I have to go look it up every time. And it is 6.67 times 10 to the negative 4th. Oops, that's not a 4, that's 11. Negative 11 Newton meter squared per kilogram squared, multiplied by the mass 1, let's call that the mass of the proton, which is 1.67 times 10 to the negative 27th kilograms. Multiply that times the mass of the electron, which is 9.11 times 10 to the negative 31 kilograms. And divide that by 1 meter. Don't forget to square it. Close parenthesis. When you do that calculation right there, you end up with a value that is 1.015 times 10 to the negative 67 newtons. So here you can see which one of these two is larger. In fact, let's take the ratio so that we can see it even more clearly. F sub E over F sub G. It's going to be on the order of 10 to the 39th. 10 to the 39th. That means that the electrostatic force, the electromagnetic force itself, is 10 to the 39th times greater than the gravitational force. Now you might say, well, that's big. Yeah, it is big, but we lose track of exactly how gigantic that number is. So let me give you an illustration. You've seen the demonstration now where you can take the glass rod, remove a few electrons from it, and pick up pieces of paper. That's an illustration right there of exactly how big this 10 to the 39th is. Because what you're doing is, with the exchange of a few electrons, you're scraping off a few electrons. Now, how do I know it's just a few? Well, because you don't see the structure of the glass rod change. If you removed half of its electrons, it would just fall apart. So it's just a few electrons. And whenever you remove those few electrons from the glass rod, well, now it becomes charged and it's able to pick up those pieces of paper and overcome the gravitational attraction of an entire planet. So Earth underneath that paper is pulling the paper downward, and the electrostatic force is pulling the paper upward, but it pulls it much more strongly and is able to overcome the gravitational attraction of an entire planet just with the exchange of a few electrons. That's how big 10 to the 39th is. So appreciate that. That's another reason why also, whenever we're working problems as we go through this class, and you can, and you know, it's said that you can ignore gravity in most of these interactions if you're talking about the electrostatic force. Well, yeah, the reason you can ignore gravity is because gravity doesn't make a difference in the calculations until like the 39th decimal place. And most calculators can't go out that far. So in most cases, not all, but most cases, you will be able to ignore the gravitational force if you're just talking about the interactions between charged particles. And the reason you can do that is because of that right there.